Hi, this is Dr. Tech talking about the exam one. As promised, I'll do this before class on Monday. I will be away for the next 2 days, so this is the last day I can do it. All right, so here's question number one. Question number one is giving you a few constraints. So the first constraint is D is a set that has these three elements, and E is a set that has these elements. Now your exact numbers may be different because I got a few sets of problems. And then we have to come up with F0, F1, D0, D1, E0, and E1 so that the following requirements are met. D has to equal to the union of D0 and D1. E has to be the same as the union of E0 and E1. F has to equal to the union of F0 and F1. F is a function. It is, well, in class I made the correction that it is not injective, but it is surjective. F0 is bijective, F1 is bijective, and then D0 is the domain of F0, E0 is the codomain of F0. And likewise, D1 is the domain of F1, and E1 is the codomain of F1. And when you look at the intersection between F0 and F1, 29, 6 as a two-tuple has to be there. The intersection of the two functions can only be exactly one, and then each function also has two elements. So now the question is, how do we figure this out? So let's see if we can use a mouse pad here to figure out the answer. All right, so I'm just resizing the window so it fits the screen. There we go. All right, so what we know at this point is 29.6 is in F0, 29.6 is also in F1. So that means if I want to look at F0 as a set, it has to consist of 29.6. And if I look at F1, it also has to have 29.6. Now they can have additional stuff. Okay, I'm just emphasizing that they can have additional stuff, but 29.6 is the is one that they both must have. So that means if I look at D0, D0 must have 29 as an element, and then D1 also must have 29 as an element. And then when I look at E0, 6 has to be one of the elements. When I look at E1, 6 also has to be one of the elements. So we have at least this much figured out just because we know that 29.6 is an element of the intersection between F0 and F1. So now the question is, how do we figure out the rest? Well, the rest, basically, most of it has to do with F0 and F1. They both have to be bijective. Okay. Oh, the other thing that I told you guys to do is to remove one of the elements in E, except for 6 in this case. So, so in this case, let's say we take 12 out. So E only has 6 and 2. Okay. So let me just write down that as well. So we have D having exactly 29, 8, 9, and then we have E having exactly just 6 and 2. There we go. All right, so given that these are the requirements, so that means, and because we know that F0 and F1, they both have cardinalities of 2, and because they're both bijective, so that means, E0 and E2, they're actually the same. They both have 6 and 2, which makes them exactly the same as E itself. Now, when you look at the D, they will be slightly different because the union of those will end up with the union of that results in a function. So that means out of the 3 elements of D, D0 is going to take care of one of the elements other than 29, and then D1 has to take care of the other one. So that means in terms of the domain, okay, this is kind of arbitrary, but you can flip, meaning you can flip these two. All right, so knowing that the domain D0 has 29, 8, so that means F0 also needs to map the other element, which is 8, to one of the other element in E, because it is known to be bijective. So 2 is pretty much the only choice here. And then we can argue the same thing for F1, which means F1 has to map 9 in this case to 2 as an element. So when you look at all of these, okay, so let's double check our constraints and see whether they all work or not. So D is the union of D0 and D1, so that will make it 29, 8, 9, and that meets the requirement. E is the union of E0 and E1, which is easy to figure out because they are exactly the same. So E is 6, 2, or has 6, 2 as elements. And then F, on the other hand, is the union of F0 and F1. So it has 29, 6, 8, 2, and 9, 2. All right, so when you look at this, it is not injective, because you can see how 2 distinct values of the domain map to the same value in the codomain, but it is surjective, because 6 and 2 are the elements in the codomain, and they're both mapped to. So this is how we figure out the answer to question number 1. All right, let's move on to question number 2. So for question number 2, okay, it's actually not that difficult once you get the hint. So the hint says, okay, let's look at yx minus g of yx minus g of xy. So once you expand these equations, one is y plus x times y plus x plus 1, the whole thing divided by 2, plus x. So that would be g of yx. And then g of xy is x plus y times x plus y plus 1, the whole thing divided by 2, plus y. Okay? So when you perform the subtraction, you can see how this term is really exactly the same as this term here, because x plus y and y plus x are exactly the same. So the actual difference is really just x minus y. So now that we know this, so that means to get to g of yx, from g of xy, we just have to add x minus y from g of xy. So that means x of xy, which in the most easy way to express is really just g of yx, is now expressed as g of xy plus x minus y. So that's the intended answer. On the other hand, if you expand this out and just express this as x plus y times x plus y plus 1, the whole thing divided by 2, and then you can simplify that whole thing and just say plus x. I will accept this as a correct final result, as well as this as the final and as a result, as a valid final result. So that's for question number 2. Now let's look at number 3. So this is question number 3. You're given a set Y with 5 elements. Choose a set of X that is a subset of Y, so that X is the largest set, such that all relations defined over X must be transitive. Okay, so let's deal with this one. So you start basically with X being the empty set, okay? So now the question is the empty set transitive? The answer is yes, okay? X is transitive. But is this the largest subset of Y that you can, over for all relations? Okay, so it doesn't matter how you define the relations, X is going to be transitive. So now you look at, what if X has one single element? Well, in that case, all relations for this particular X has to be transitive too, because how many relations can you make out of this? Let's try to find out. Okay, R can be empty, and since you only have one element, R can also have 30 relating to 30, and that's it. This is transitive because nothing proves that it is not transitive, and this is transitive as well because once again nothing can prove that it is not transitive, and that's it. So now you can say, okay, what about if I add one more? Okay, if I add one more to it, what can R be? Well, R can be empty, but we know that empty relation is already transitive for over any set, so that's kind of easy to figure out. So now you can say, what if R has 30, 30, and 24, 24? That is transitive. What if R has 30, 24, and that's it? Is that transitive? The answer is yep, it is transitive. So now the next question is, what if R has 30, 30, and 30, 24? Is that transitive? Well, it is still transitive. What if R has 30, 30, 24, 30? It is still transitive. Transitive. What if R has 30, 30, 24, 30, 24, 24? It is transitive. In other words, you cannot make it not transitive, because we remember that in to make something transitive, you're basically looking for something like this. You're saying that ARB and BRC, it has to imply that ARC. So this means if you cannot find a situation to make the left hand side true but the right hand side false, then the relation is transitive. With only two elements in the set, with two distinct elements in the set, you just cannot make it happen. Let me think about this. Actually, you can make it happen. Oh, okay. You can make it happen. Let me show you why it is possible. So you can have 24, 30 and 30, 24. Oops. This is not transitive because in this case ARB, okay, ARB, A being 24, B being 30, satisfies this requirement, and then have B being 30 and C being 24 again is going to meet this requirement. So now we have the left hand side of the implication being true, but 24, 24 is not in the set, so that makes it not transitive. So that means the largest set the largest set that all relations defined over X has to be transitive means that X only has one element. There we go. So that's the answer. Now, but that's not the only part of the answer that is, well, actually I answered the second part as well. The second part is to add one more element to X so it becomes Z, so that you can define the relation S over Z so that S is not transitive. This is our S here, and this is our Z here. So this way we can prove that when you have a set of two elements or more, then you can no longer claim that all relations defined over this particular set has to be transitive. So just change. Those can all be R, but this one has to be S because it is not transitive. So that answers question number 3. Oh, you cannot see the last one, sorry about that. This is the requirement of being transitive, and as I said, if A is 24, B is 30, and then C is 24 again, then 24, 24 is not in the set, and therefore this particular relation defined over Z is not transitive. All right, moving on to question number 4. Okay, so let's check out question number 24. So 24 is asking you to give me a scenario where x is 2, 11. Okay, so we need to look for a case where it is symmetric and anti-symmetric. Well, that's an easy one. R is 2, 11, 11, 2. This is symmetric because 2, 11, 11, 2 are both here, so it is symmetric. But it is, it is not anti-symmetric. Okay, I need to change this to make it okay. That is symmetric and anti-symmetric at the same time. Okay, that's the easy one because we talked about the empty relation in class quite a bit, and we know that the empty relation is both symmetric and anti-symmetric in class. Okay, next one is symmetric and not anti-symmetric. Okay. All right, so this is the opposite of the first one. This is going to be symmetric because 2 R11 if and only if 11 R2, and for everything for all the other pairs, they do not exist, which is fine because if one is missing, the other one has to be missing. So it is symmetric, but it is not anti-symmetric because anti-symmetric says that if A are B and B are A, then A and B must be the same. Well, guess what? We got A R B here, we got B R A here, but 11 and 2 are not the same. So it is symmetric but not anti-symmetric in this case. Next one, not symmetric and anti-symmetric. Okay, this one is actually easy as well. That, done. Okay, why? Because this is not symmetric, because if 2 are 11, in order for relation to be symmetric, then 11, 2 has to be in the relation as well. Since it's missing, it is not symmetric. But it is anti-symmetric because we cannot find a case where 2, 11, 11, 2 are both in the relation, and since the left-hand side of the relation is false, that means the entire implication. Well, since the left-hand side of the implication is false, that means the entire implication itself is true. So this particular relation is anti-symmetric. So the last one is not symmetric and not anti-symmetric. Okay, let's check this one out. So if something is not symmetric, can we make it so that it is not anti-symmetric? Well, generally speaking, it is possible, but we'll need 3 elements to make it happen. Because what we need is to make it so that ARB and BRA do exist for two elements in X, but we also have one other pair of elements where we only have ARB but not BRA. But if we only have 2 elements, then it cannot happen. Because in order for something to be not symmetric, that means only ARB or ARB is there, but BRA is not there. So the proof or the argument that this is not anti-symmetric and not symmetric is to basically enumerate every single possible way, and then say that, well, these are only for one of the first three cases, but and once we have exhausted all of those cases, then we have no cases left. So to do that, we basically say we spell out every single relation that is symmetric but not anti-symmetric, and this is the only one that I can think of. Symmetric and anti-symmetric, we have empty, and then we have 2, 2, 11, 11. that's also symmetric and anti-symmetric. We cannot have anything that involves 211 or 11.2, so that's basically all that we can do here. When we look into not symmetric and anti-symmetric, then we have R also being 11.2. And we can certainly include reflexive elements in here too. So we can have 211, 22, 211, 22. There we go. 22, 11, 11, and of course we have the other one 2, 2, 11, just 11, 11 itself, and then you basically have to repeat these for 11.2. But you can also prove this in another way, because symmetric is this. Symmetric says, you know, for all AB, okay, AB in X, A R B if and only if B are A. Okay, that's symmetric. This is for symmetry. And then for anti-symmetric, it says for all AB in X, ARB and BRA implies A equals B. This is for anti-symmetric. Oh, sorry about that. I keep typing where you cannot see. Okay, that's again, I think that can be very annoying. All right, so that means, you know, in this case, we have to find at least one case where this is not true, and at the same time, we have to find one case where this is not true. It's not difficult to make one of those two happen, but if they're both happening, let's see what happens. Okay, so you have to find one case where ARB, if and only if BRA is false, and you only have two elements. That means, you know, one of them has to exist where the other one is missing. So that means, you know, we have a scenario of this or that. Okay, and also R is okay, I'm just gonna enumerate all of these just so that we are clear that okay. All right, so we got these. That makes it not symmetric. Now, to make it not anti-symmetric, we need this to be true. We need this to be false. Okay, to make it not anti-symmetric, we need this to be false. And the only way to make an implication false is to have the first part being true, but the second part being false. But we can see how, you know, they're contradictory, because to make this true is to make this true too. So since we have to make this false, and in the case of two elements, there are only two ways to make this false. And once you make this false, then, you know, we cannot make this true anymore. So as a result, you know, they cannot both be true. So you can argue that way, but you can also just enumerate every single case here, because, you know, if you look at all of these relations, we have actually exhausted every single way to define relations when we only have two elements. So that's kind of the proof for this question. Question 5. So for question 5, we want to define the minimal relation R over X for the following cases. R is partially ordered and R is totally ordered. Okay, so let's see how we can do that. So R is partially ordered. Okay. So if R only needs to be partially ordered, remember we need it to be reflexive, we need it to be anti-symmetric, and also transitive. That's pretty easy. R only has 4, 4, 20, 20, and then 23, 23. That makes it partially ordered. And it's as small as it can get, because if you drop any one of these elements, it's no longer reflexive, and that's a requirement to be partially ordered. So the next one is R is totally ordered. So in order for R to be totally ordered, it first has to be partially ordered. So we need all of these. Okay. But we also need it so that every relation is every element is related to another element, any other element in the set. So that means we have to kind of include 420 and then 423 in it. Okay, but once we introduce these, it also has to be transitive. So that means oh, okay, let me put this here. So 20 also has to relate to 23, like that. Okay, so this makes every element relate to every other element in one way or another. Okay, but then you look at this and go like, are we, let's see, 4, 4, 420, 423, 20, 20, 20, 23, 23. Oh, this is it. This is done. Basically, this relation is less than or equal to, because we know that less than or equal to is totally ordered. And this is the minimal too, because if you drop any one of these, then you have the problem of an element not relating to another element in the set. So that's totally ordered. All right, moving on to question 6 of 6. All right, so in question 6 of 6, it's asking, oh, okay, this one is great. So A in this case is basically the set of integers of 5, 6, 7, and so on. Okay, so now the first one is A is a subset of n is true. Why? Because every element of A is in the natural number, but not the other way around. That makes A a proper subset of n. Okay, so you can either write it in English, or you can write it in symbols. So you can basically say for all x in A, for all x in A implies x in n. Okay, that makes it a subset, but at the same time we also have some unique items, right? So that means we can find, well, in this case we can say like 2. Okay, 2 is in n but not in A, so that's why A is a proper subset of n. Then the next question is, what is the value of bar A bar equals to aleph null? So bar A bar equals to aleph null is true. Then we have to explain that. Okay, so the way to prove or explain or argue for this is to make a function. So we basically say, let's define a function f, and f maps A, which is our domain, to the codomain, which is n, which is the set of all natural numbers. Well, just because we can we claim there's a function, doesn't mean it's done, so we have to make it happen. So f is basically f of x is, in this case, x minus 5. So if f of 5 is 0, f of 6 is 1, and so on. So now you can see how f is mapping every element of A to elements in N. So now the question is f bijective? Okay. Well, there are two ways to make it, to prove that it's bijective. You can either say that there's an inverse function, so you can say f inverse is x plus 5. So the fact that it has an inverse function kind of means that it is bijective. So that's pretty easy to argue. The other thing you can also argue is to say, given x does not equal to y, then f of x does not equal to f of y, because x plus 5 does not equal to y plus 5. Okay, so you can argue that. That makes it injective. Once you prove that it's injective, you also have to make sure that it is surjective. So surjective basically says, given any n, m in n as a natural number. Okay, I'm writing where you cannot see again. Oh man, this is awful. So given any m in n, m plus 5 maps to m. Let me see. Yes, in f, using f. So that's that makes it surjective. So now that we know it is injective and also surjective, then we know that f is bijective. So now we say, because f is a bijective function mapping A to n, the cardinality of A and n are the same, but the cardinality of n is the definition, definition of aleph null. So that's basically the entire proof. All right, so we are all done here. I'm going to stop the recording and make it public.